Tonight, we're going to stand next to the largest stars in the observable universe. Not describe them from a safe distance. Not look at them through a telescope and quote statistics. Stand next to them. Place them in our solar system and watch what happens. Understand them from the inside out. What they are made of, how they were born, how they burn, and most importantly, how they die. Because the largest stars in the universe don't just die. They don't fade gently like our sun will one day fade. They explode. They collapse. They release more energy in a single second than our sun will produce across its entire 10 billion year lifetime. They forge the heaviest elements in existence in the last moments before they destroy themselves. They leave behind objects so extreme, neutron stars, black holes, that the physics describing them pushes against the edge of what our best theories can describe. And they are terrifying not because they threaten us. They don't. They're so far away that their deaths have no direct effect on Earth. They are terrifying because of what they reveal about the universe, about the scale of things, about how extreme the cosmos is when it operates without restraint, about what matter becomes when gravity has nothing to push against. By the end of tonight, you're going to understand exactly how large the largest stars are, what that size means physically, why being large is both a superpower and a death sentence, and what happens when stars hundreds of times more massive than the sun finally run out of road. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Let's start by establishing what the sun actually is, because most people wildly underestimate it. The sun is not a medium-sized star in the way that medium suggests ordinary or unremarkable. By mass, the sun is larger than approximately 90% of all stars in the Milky Way. Most stars are dim red dwarfs, objects far smaller and cooler than our sun, burning hydrogen so slowly that some of them will still be burning billions of years after every other type of star has gone dark. The sun has a radius of approximately 696,000 kilometers. That is 696 million meters. That number is almost impossible to feel intuitively. So let's try to build the intuition correctly. Earth has a radius of about 6,371 kilometers. The sun's radius is approximately 109 times larger than Earth's radius. If you replaced Earth with the sun would extend more than halfway to the moon. If you put Earth at the center of the sun, you could fit 1.3 million Earths inside the sun's volume. Not on its surface, inside it. The sun's mass is approximately 1.989 times 10 to the power of 30 kilograms. That's a 2 followed by 30 zeros in kilograms. The sun contains roughly 99.86% of all the mass in the entire solar system. Every planet, every moon, every asteroid, every comet, every piece of dust, every atom of gas in the entire volume of space, from here to the outer edge of the solar system, all of it combined, is only about 0.14% of the total mass of the solar system. Everything else is the sun, and the sun is not the largest star, not even close. This is where the scale problem becomes almost philosophical. Because stars that are large by stellar standards are not large in the way that a large mountain is large compared to a hill. They are large in a way that requires you to rebuild your intuition from scratch and accept that you're not going to be able to picture this correctly. You are going to hear the numbers, you are going to do the comparisons, and some part of your brain is going to refuse to fully believe them. That's fine. The numbers are still true. Let's build up to the largest stars in steps, because going directly to the maximum is like trying to understand the distance to the edge of the observable universe by starting with the distance to your front door. The steps matter. Stars are not all born equal. They form from collapsing clouds of gas and dust, molecular clouds, and the amount of material that ends up in any given protostar is partly a matter of the local conditions in the cloud and partly a matter of something that looks a lot like luck. The smallest stars that can sustain hydrogen fusion, that can actually ignite and burn in the way we recognize as a star, have masses of approximately 0.08 solar masses. About 8% of the Sun's mass. These are red dwarf stars, M-type main sequence stars, and they are by far the most common type of star in the galaxy. The very smallest red dwarfs are barely larger than the planet Jupiter. They burn so slowly, at temperatures so low by stellar standards, that some of them will burn for trillions of years. The universe is only 13.8 billion years old. No red dwarf has ever burned out naturally. Not one. Every red dwarf that has ever formed is still burning today. A star with about half the Sun's mass burns somewhat hotter and somewhat brighter. It will live for perhaps 50 billion years, much longer than the universe's current age. A star with exactly the Sun's mass, our own star, lives for about 10 billion years. We're halfway through. A star with 2 solar masses burns roughly 16 times more luminously than the Sun. It lives for perhaps 1 billion years. A star with 10 solar masses burns about 10,000 times more luminously than the Sun. It lives for perhaps 20 million years. A star with 30 solar masses burns perhaps 200,000 times more luminously than the Sun. It lives for only a few million years. Notice the pattern. As you go up in mass, luminosity increases dramatically, but lifespan decreases dramatically. More massive stars burn their fuel faster in proportion to how much fuel they have. They live fast and die young. This pattern, understood for most of the 20th century, tells us something fundamental about what stellar mass means for a star's fate. Mass is destiny. But the mass range doesn't stop at 30 solar masses. It extends much further. And the stars at the upper end of that range are where the universe stops behaving in any way that feels remotely familiar. The most massive, most luminous, and hottest main sequence stars are called O-type stars. They are designated by the letter O in the Harvard Spectral Classification System, which ranks stars from hottest to coolest using the letters O, B, A, F, G, K, M from hottest to coolest. Our Sun is a G-type star. O-type stars are at the absolute top of the temperature sequence. An O-type star has a surface temperature between 30,000 and 60,000 degrees Kelvin. For reference, the Sun's surface temperature is approximately 5,500 degrees Kelvin. O-type stars are between 5 and 11 times hotter than the Sun at their surfaces. At those temperatures, they radiate primarily in the ultraviolet portion of the electromagnetic spectrum. To human eyes, they would appear blue-white, a piercing, harsh blue-white, unlike the warm yellow of our Sun. O-type stars are extraordinarily rare. They make up only about 0.00003% of all stars in the Milky Way. Out of the estimated 200 to 400 billion stars in our galaxy, perhaps only a few tens of thousands are O-type stars. Their rarity is a direct consequence of their extreme luminosity. They pour out energy so prodigiously that they burn through their hydrogen fuel at a rate that allows only short lives by stellar standards. Even the least massive O-type stars, those near the lower boundary of about 16 solar masses, are already extraordinary objects. They have radii roughly 6 to 10 times the Sun's radius. Their luminosity is on the order of 30,000 to 100,000 times the Sun's luminosity. In a single day, such a star produces more energy than the Sun produces in several years. But the O-type stars we're describing here, impressive as they are, represent only the beginning of what the upper end of the stellar mass spectrum contains. The most massive O-type stars, those pushing toward 100 solar masses and beyond, enter a different category of existence. They are luminous enough that the radiation pressure from their own light begins to push their outer layers outward with forces comparable to or exceeding the inward pull of gravity. This is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who derived it in 1921. The Eddington limit is the maximum luminosity a star of a given mass can sustain before radiation pressure exceeds gravity and blows the outer layers away. For a star of 100 solar masses, the Eddington luminosity is approximately 4 million times the Sun's luminosity. Stars near and above this limit lose mass at extraordinary rates, shedding their outer layers through powerful stellar winds. This is a critical point. The most massive stars are fighting a constant battle between the energy they produce and the gravity trying to hold them together. They are, in a very real sense, always on the verge of blowing themselves apart. One of the most dramatic consequences of extreme stellar mass is a class of objects called Wolf-Rayet stars, named after the French astronomers Charles Wolf and Georges Rayet, who discovered them in 1867. Wolf-Rayet stars are what happens when a massive star's outer hydrogen envelope is completely blown away by its own radiation and stellar wind, exposing the hot, dense inner layers directly to space. A Wolf-Rayet star is not a single type of object in the way that a red dwarf is a single type. It's a stage in the evolution of the most massive stars, and it comes in several varieties depending on what layer of the original star's interior has been exposed. WN stars show nitrogen and helium on their surfaces. WC stars show carbon and helium. WO stars, the rarest, show oxygen prominently. Each variety tells us how deep into the original star's structure we're looking. What makes Wolf-Rayet stars extraordinary, beyond the simple fact that they've lost their outer envelopes, is their wind. The stellar wind, from a Wolf-Rayet star, the stream of charged particles flowing outward from the surface, is one of the most violent outflows in the non-exploding universe. Where the Sun loses about 1 solar mass every 100 trillion years through its gentle solar wind, a Wolf-Rayet star can lose 1 solar mass every 100,000 years. 1 million times more mass loss per unit time. The wind from a Wolf-Rayet star reaches speeds of 1,000 to 3,000 kilometers per second. 3,000 kilometers per second, is 1% of the speed of light. The solar wind, by comparison, reaches about 500 kilometers per second. Wolf-Rayet winds are up to 6 times faster than the sun's wind and carry vastly more mass. The nebulae formed by Wolf-Rayet winds are spectacular. The star blows out a bubble of material that can extend for tens of light years in every direction. The material is enriched with carbon, nitrogen, oxygen, and other heavy elements processed in the star's interior and mixed to the surface by convection. Wolf-Rayet nebulae are some of the most chemically interesting environments in the galaxy. Perhaps the most famous Wolf-Rayet star visible to the naked eye from the southern hemisphere is Gamma Velorum, part of the Vela constellation. It's a binary system containing a Wolf-Rayet star and a massive O-type companion. The Wolf-Rayet component in Gamma Velorum has a mass of about 9 solar masses today, after losing enormous amounts of mass through its wind, and began with perhaps 30 solar masses or more. It has already shed most of its original mass in the violent Wolf-Rayet phase. Wolf-Rayet stars represent massive stars in the process of destroying their own outer layers, preparing themselves for the most violent event in stellar evolution. They are already dying in the sense that every solar mass they shed through the wind is a solar mass that never reaches the supernova explosion. They are pre-explosive, unwinding themselves, discarding layer after layer of material, until what remains is a hot, dense, rapidly evolving core that will eventually detonate. Above the Wolf-Rayet stars in terms of luminosity, though the categories overlap and interconnect in complicated ways, lies a class of stars called hypergiants. The word hypergiant is not casual. It is a specific astronomical designation for stars that exceed a luminosity threshold of about 100,000 times the sun's luminosity, and it describes some of the most extreme objects in the observable universe. Hypergiants are divided into several subclasses, depending on their color and temperature. Blue hypergiants, yellow hypergiants, red hypergiants. The color tells you where the star is in its evolutionary cycle and how it's currently configured. A massive star can be a blue hypergiant early in its life, evolve to a yellow hypergiant, then become a red hypergiant in its later stages, and possibly become a Wolf-Rayet star before it finally explodes. The exact evolutionary path depends on the star's initial mass, its metallicity, which refers to the abundance of elements heavier than hydrogen and helium in its composition, and other factors. The luminous blue variables, often abbreviated LBV, represent one of the most dramatic categories of hypergiant. These are massive, extremely luminous stars that are inherently unstable, undergoing dramatic outbursts and changes in brightness and size over time. They are stars caught in a phase of particularly intense instability near the Eddington limit, where even small perturbations to their internal structure can trigger massive outflows of material. The most famous luminous blue variable, and one of the most extraordinary stars known to exist anywhere in the observable universe, is Eta Carinae. Eta Carinae sits about 7,500 light-years from Earth in the constellation Carina. At that distance, it is not a particularly dramatic object to the naked eye today, appearing as a dim star in the southern sky. But in 1843, something happened to Eta Carinae that made it briefly the second brightest star in the night sky, exceeded only by Sirius. Eta Carinae erupted. Between 1837 and 1858, in what astronomers now call the Great Eruption, Eta Carinae dramatically increased in brightness and ejected an enormous amount of mass into the surrounding space. At its peak in April 1843, it reached an apparent visual magnitude of -0.8, making it one of the brightest stars visible from Earth. Ships navigating the southern hemisphere used it as a navigational reference point, comparable in brightness to some of the most prominent stars in the sky. And then it faded. Over the following decades, it dimmed dramatically, eventually disappearing from naked eye visibility entirely by the 1880s. By the late 19th century, Eta Carinae was a dim, obscured object, hidden behind the cloud of material it had ejected during the eruption. What is Eta Carinae? We now know it's actually a binary system, two extraordinarily massive stars orbiting each other. The primary star, Eta Carinae A, has a mass of approximately 150 to 200 solar masses. It is one of the most massive stars known in the Milky Way. Its luminosity is approximately 5 million times the Sun's luminosity. 5 million suns of light, all pouring from a single star. The companion, Eta Carinae B, is itself a massive O-type star of perhaps 30 to 80 solar masses, with a luminosity of perhaps 1 million times the Sun. The Great Eruption of the 1840s was not a full supernova. The star survived. What it ejected became the Homunculus Nebula, a pair of expanding lobes of gas and dust now extending about a quarter of a light year in either direction from the central star. Still expanding, still visible through infrared telescopes because the dust within the nebula glows from the energy it absorbs. The homunculus contains roughly 10 to 40 solar masses of material, ejected in a period of about 20 years. A star ejected up to 40 solar masses of material rapidly enough that we can describe it as an eruption, and survived. This alone tells us something extraordinary about the scale of Eta Carinae. 10 to 40 solar masses is more than most stars in the galaxy contain in total. Eta Carinae expelled that much material and continued burning. The current luminosity of Eta Carinae makes it one of the most luminous stars in the Milky Way. Infrared observations that can penetrate the dust nebula reveal the star itself to be pouring out energy at roughly 5 million solar luminosities. By another measure, its bolometric luminosity, accounting for all wavelengths of radiation, including the ultraviolet that is absorbed by the surrounding dust, may be even higher. Eta Carinae is almost certainly a pre-supernova object. When it explodes, it will be visible from Earth in daylight for weeks. It may produce what's called a hypernova, an explosion 10 times or more energetic than a standard core collapse supernova. It may even produce a gamma-ray burst, one of the most energetic events in the universe, though the orientation of its rotation axis makes it uncertain whether any gamma-ray beam would be directed toward Earth. When will it explode? We don't know precisely. It could happen in 100 years. It could happen in 100,000 years. On astronomical timescales, it's imminent. On human timescales, it's unpredictable. But Eta Carinae is one of the best candidates for the next spectacularly dramatic stellar death visible from Earth. And it is teaching us an enormous amount about what happens to stars of extreme mass in the most violent phases of their evolution. In the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a distance of about 160,000 light-years, there is a stellar nursery called 30 Doradus, also known as the Tarantula Nebula. It is the most active star-forming region in our galactic neighborhood, a turbulent, blazing region of gas and dust being heated and ionized by the fierce radiation of the young, massive stars forming within it. At the center of the Tarantula Nebula is a dense cluster of extraordinarily massive stars called R136. And at the center of R136 is one star that stands apart from all the others, R13601. R13601 is the most massive star currently known to exist in the observable universe. Though the distinction comes with uncertainty and ongoing scientific debate, its mass has been estimated at approximately 215 solar masses in recent studies, with some earlier estimates ranging from 265 to 315 solar masses. The uncertainty reflects the genuine difficulty of measuring stellar masses at extreme values. Regardless of the precise number, R13601 is in a mass range that represents the absolute upper boundary of stellar mass as we understand it. Its luminosity is approximately 8.7 million times the luminosity of the Sun. To put that in perspective, if you replaced our Sun with R13601, the increase in energy reaching Earth would be so extreme that the oceans would evaporate in minutes. The atmosphere would be blasted away. The surface temperature would climb to thousands of degrees. Earth would become, in a matter of days, an uninhabitable, airless rock. Not because of any violent explosion, simply because the star at the center of our system would be emitting nearly 9 million times more energy than what we currently receive. R13601's surface temperature is approximately 46,000 degrees Kelvin, roughly 8.5 times hotter than the Sun's surface. At this temperature, the peak of its emission is in the far ultraviolet, radiation energetic enough to ionize hydrogen atoms throughout a vast surrounding region. R13601 is the primary ionizing source for the entire Tarantula Nebula, which spans more than 600 light-years. One star, ionizing a region bigger than the distance to most of our nearest stellar neighbors. The radius of R136A1 is approximately 35 solar radii. This sounds large, but it's actually not enormous in the category of largest stars by size. R13601 is compact for its mass, extraordinarily massive, enormously luminous, intensely hot, but not the largest by physical size. This is because it's a young, hot star still on the main sequence, not yet in the bloated giant phase that some less massive but more evolved stars have reached. R13601 is losing mass at a catastrophic rate. Its stellar wind, driven by the pressure of its own radiation, is stripping away the outer layers continuously. Current estimates suggest it loses material at a rate roughly 10 million times faster than the Sun loses mass through its solar wind. It was probably born even more massive. Some estimates suggest its initial mass may have been as high as 300 solar masses or more. It has already shed a significant fraction of its original mass and will continue to shed mass rapidly throughout what remains of its short life. How short is that life? R13601 is estimated to be approximately 1 million years old, which means it had probably already lived through more than a third of its total lifespan. Stars this massive live only about 2 to 3 million years. R13601 will likely explode as a hypernova within roughly 1 to 2 million years. On an astronomical timescale, it is nearly finished. When it dies, what will it leave behind? The answer to that question depends on how much mass it retains at the moment of core collapse. If it retains enough, perhaps more than about 25 solar masses, the collapse may produce a black hole directly, with little or no visible explosion at all. The star might simply wink out, its outer layers falling inward without a significant outward energy release, because the core collapse proceeds so rapidly and completely that even the powerful shockwave of a supernova cannot escape. These are called failed supernovae, or collapsar events. Alternatively, if mass loss through its wind strips R13601 down to a smaller mass before it collapses, it might produce a more traditional hypernova, an explosion vastly more energetic than a conventional core collapse supernova. The energy released could produce a gamma-ray burst, a beam of gamma radiation detectable across the observable universe. R136A1 is 160,000 light-years away. Its death will not threaten Earth in any meaningful sense. But if it produces a gamma-ray burst, and if the beam happens to point in our direction, the gamma radiation reaching Earth would be significant. Not civilization ending at that distance, but detectable. Worth studying, perhaps with enough energy to cause measurable effects in the upper atmosphere. We're watching it, we're measuring it, and in a relatively short time, by astronomical standards, we'll watch it die. R13601 is the most massive known star, but the largest stars by physical size, by radius and volume, are not necessarily the most massive. The stars that hold the size records are red and yellow hypergiants, objects that have expanded to enormous radii in their late evolutionary phases. Let's meet them. UY Scuti is often cited as one of the largest known stars by radius. It's located in the constellation Scutum, about 9,500 light-years from Earth. UY Scuti is a red supergiant, a pulsating variable star that changes in brightness and size over time. At its maximum, its radius has been estimated at approximately 1,700 solar radii. Some estimates push this to 1,900 solar radii. What does 1,700 solar radii mean in terms you can hold in your mind? The solar radius, as we established, is 696,000 kilometers. Multiply that by 1,700 and you get approximately 1.18 billion kilometers. UY Scuti's radius is approximately 1.18 billion kilometers. The distance from Earth to the Sun is about 150 million kilometers. UY Scuti's radius is nearly 8 times the Earth-Sun distance. If you placed UY Scuti at the center of our solar system, its surface would extend past the orbit of Jupiter. Not to Jupiter, past it. Jupiter orbits the Sun at an average distance of about 778 million kilometers. UY Scuti's surface, if it were in our Sun's position, would engulf Mercury, Venus, Earth, Mars, the asteroid belt, and extend deep into the outer solar system, past Jupiter. But UY Scuti is not the only contender. Stephenson 2-18, also known as ST2-18, is another red supergiant located in the open cluster Stephenson 2, about 19,600 light-years from Earth. It has an estimated radius of approximately 2,150 solar radii. If the estimate is correct, Stephenson 2-18 would be larger than UY Scuti. Its surface, if placed at the Sun's position, would extend roughly to the orbit of Saturn. Saturn orbits the Sun at an average distance of about 1.4 billion kilometers. The radius of Stephenson 2-18 by these estimates is approximately 1.5 billion kilometers. Let's think about what that means for light travel time. Light, the fastest thing in the universe, travels at 300,000 kilometers per second. It takes light about 8 minutes to travel from the Sun's surface to Earth. It takes light about 43 minutes to travel from the Sun to Jupiter. It takes light about 80 minutes to travel from the Sun to Saturn. It would take light approximately 85 minutes to travel from the center of Stephenson 2-18 to its surface. A beam of light, starting at the center of this star and moving outward at the speed of light, would take an hour and 25 minutes to reach the star's surface. A beam of light would take nearly 2 hours to cross Stephenson 2-18 from one side to the other. Our Sun, by comparison, has a light travel time from center to surface of just over 2 seconds. Stephenson 2-18 is between 1,300 and 1,500 times the diameter of our Sun. If you tried to line up suns across the diameter of Stephenson 2-18, you would need more than 1,000 of them. VY Canis Majoris, a red hypergiant in the constellation Canis Major, about 3,900 light-years from Earth, has been intensively studied for decades and was for a long time considered the largest known star. Recent measurements have revised its size somewhat downward to approximately 1,420 solar radii. Though the uncertainty in such measurements is significant, VY Canis Majoris is surrounded by one of the most complex and beautiful nebulae created by a non-exploding star. It is losing mass at an extraordinary rate, with knots, arcs, and filaments of ejected material extending across vast distances around it. The nebula reflects the star's light and has been mapped in detail, showing a history of repeated asymmetric mass ejection events that tell us the star has been unsteady and turbulent throughout its recent history. DWOH G64, located in the Large Magellanic Cloud at a distance of about 168,000 light-years, is another red hypergiant with an estimated radius of approximately 1,540 solar radii. It is surrounded by a thick torus of dust and gas, a ring of material in the plane of its equator, suggesting that much of its mass loss has occurred preferentially in that direction. The dust is thick enough to obscure most of its visible light. But infrared observations reveal it clearly. Mu Cepae, known as the Garnet Star because of its distinctly reddish color visible to the naked eye, is a red supergiant in the constellation Cepheus, about 5,600 light-years away. It has a radius of roughly 1,650 solar radii and a luminosity of approximately 350,000 solar luminosities. It's one of the largest stars visible without a telescope from the northern hemisphere, and its characteristic reddish tint has been noted by observers for centuries. These stars, all of them red supergiants and red hypergiants, are at completely different points in the stellar evolutionary story compared to R13601. They began life as massive O-type or B-type stars, burned through their core hydrogen relatively quickly, and then expanded enormously as their internal structure changed. They are, in stellar evolutionary terms, old, near the end. The expansion to enormous radii is part of the dying process. The color of a star tells you its surface temperature. Red stars are cool by stellar standards. Blue stars are hot. This relationship is not a coincidence. It's a direct physical consequence of how matter emits radiation. All objects with temperatures above absolute zero emit electromagnetic radiation. The spectrum and intensity of that radiation depends on the temperature of the object. Cooler objects emit more radiation at longer wavelengths toward the red end of the spectrum. Hotter objects emit more radiation at shorter wavelengths toward the blue end. When a massive star like UY Scuti or Stevenson 2-18 appears red, it's telling us its surface temperature is around 3,000 to 4,000 degrees Kelvin, far cooler than the surface of our Sun at 5,500 Kelvin, far cooler than the blazing 46,000 Kelvin of R13601. These stars are cool at their surfaces, despite being orders of magnitude larger and more luminous overall. The reason for this is one of the most important stories in stellar physics. When a massive star exhausts the hydrogen in its core, it faces a crisis. For its entire main sequence life, the star has been maintained in equilibrium by the pressure of nuclear fusion pushing outward against the weight of the overlying layers pushing inward. When core hydrogen runs out, that equilibrium breaks. The core contracts under gravity. The layers above it begin to fall inward. As the core contracts, it heats up. The compressed material in the core becomes hotter and denser. This heat is conducted outward into the layer of hydrogen immediately surrounding the core, the hydrogen shell. That shell of hydrogen is not in the core, has not been fusing, has been sitting there during the entire main sequence phase. Now the contracting core heats it to fusion temperatures. Shell hydrogen fusion ignites. Shell fusion produces energy, lots of energy, more than the core was producing in its final days. And that energy pushes outward on the overlying layers. But instead of simply maintaining the previous equilibrium, the enormous energy of shell fusion drives the outer layers outward. They expand dramatically. The outer envelope of the star inflates. As the outer layers expand, they cool. The same total energy is now spread over a vastly larger surface area. The surface temperature drops. The star reddens. It becomes a red giant, or in the case of the most massive stars, a red supergiant or red hypergiant. This is why the color red, in the context of the most massive stars, signals a late and violent phase of their evolution. A blue massive star is burning hydrogen efficiently in its core and is in the relative prime of its life. A red massive star has already burned through its core hydrogen and is in the process of evolving rapidly toward its end. The timescales are very different for different mass stars. Our Sun will take billions of years to exhaust its core hydrogen and become a red giant. A star of 30 solar masses will exhaust its core hydrogen in about 7 million years and enter the red giant phase. A star of 100 solar masses might spend only 2 million years on the main sequence before expanding toward the red hypergiant phase. And the red hypergiant phase itself does not last long. Stars in this phase are unstable, pulsating, losing mass rapidly, evolving quickly. The red hypergiant phase for the most massive stars may last only tens of thousands to a few 100,000 years. They expand, lose mass, possibly contract back toward a hotter configuration, possibly expand again, and eventually reach the end of their nuclear fuel and explode. Let's go inside one of these stars, not to the surface, to the core. The nuclear burning history of a massive star is one of the most dramatic sequences in nature. It proceeds in stages, each stage burning a different element, each stage shorter than the last, each stage releasing less energy per unit mass than the one before it, and each stage producing heavier elements as the ash of nuclear burning becomes the fuel for the next stage. Stage 1 is hydrogen burning, the proton-proton chain, and, in massive stars, primarily the CNO cycle, which uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium. In the most massive stars, hydrogen burning in the core is extraordinarily rapid. A star of 100 solar masses burns through its core hydrogen in perhaps 2 million years. The product of hydrogen burning is helium. The core fills with helium ash. When the hydrogen runs out, the core contracts and heats until helium can fuse. Stage 2 is helium burning. At temperatures of about 100 million degrees Kelvin, helium nuclei can fuse. The triple alpha process combines 3 helium nuclei to form 1 carbon nucleus. Carbon can then capture another helium nucleus to become oxygen. The core fills with carbon and oxygen. For a massive star, helium burning lasts on the order of a few 100,000 years. Stage 3 is carbon burning. The carbon and oxygen core contracts further, reaching temperatures of about 600 million degrees Kelvin. At these temperatures, carbon nuclei can fuse with each other, producing neon, sodium, and magnesium. Carbon burning in a massive star lasts on the order of a few hundred to a few thousand years. It is already extraordinarily brief by any human standard. Stage 4 is neon burning. At about 1.2 billion degrees, neon nuclei begin photodisintegrating, breaking apart under the intense radiation, releasing helium nuclei that are immediately absorbed by other neon nuclei to form magnesium and oxygen. Neon burning lasts about a year or less. Stage 5 is oxygen burning. At about 1.5 billion degrees, oxygen nuclei fuse together, producing silicon, sulfur, phosphorus, and other elements in the silicon group. Oxygen burning in a massive star lasts perhaps a few months. Stage 6 is silicon burning. At temperatures exceeding about 3 billion degrees Kelvin, silicon nuclei participate in a complex series of reactions called silicon burning, which proceeds through a cascade of photodisintegration and recapture reactions, working through a series of intermediate nuclei and ultimately producing iron group elements, predominantly iron, nickel, and cobalt. Silicon burning in a massive star lasts approximately 1 to a few days. 1 to a few days. In the last few days of its multi-million-year life, a massive star is burning silicon in its core, working furiously through the last available nuclear fuel, producing iron in the innermost layers while simultaneously, in successive shells surrounding the core, it's burning oxygen, carbon, helium, and hydrogen in concentric layers like an onion. Each shell burning a different element, each contributing energy to keep the star going for its last days. And then the iron core reaches a critical mass. Iron is the end of the road for nuclear fusion. Fusing nuclei lighter than iron releases energy because the products are more tightly bound. But iron is the most tightly bound nucleus in existence. Fusing iron does not release energy. It requires energy. The star's nuclear engine, which has kept it alive for millions of years through hydrogen, helium, carbon, neon, oxygen, and silicon burning, has run out of ways to generate energy. The iron core grows. When it reaches approximately 1.4 solar masses, the Chandrasekhar limit. Gravity overwhelms every form of pressure that could support the core against collapse. What happens next happens fast. The collapse of the iron core is one of the fastest and most violent events that occurs outside of the Big Bang. In a fraction of a second, less time than it takes to blink, the iron core collapses from roughly the size of Earth to a sphere roughly 10 to 20 kilometers in diameter. The outer radius shrinks from about 6,000 kilometers to about 15 kilometers. This is not a gradual collapse. It is effectively instantaneous on any human timescale. The collapse is driven by gravity overcoming the electron degeneracy pressure that was holding the core up. As the core density climbs past about 10 to the power of 12 grams per cubic centimeter, 1 trillion grams per cubic centimeter, electrons are forced together with protons to form neutrons through inverse beta decay. The core converts from a mixture of iron nuclei and electrons to a ball of pure neutrons. The neutrinos produced by this process, billions upon billions of them, stream outward. The neutron ball reaches nuclear densities about 2 times 10 to the power of 14 grams per cubic centimeter. At this point, the strong nuclear force, which binds neutrons together in nuclei, provides an enormously stiff resistance to further compression. The neutron ball bounces. The infalling outer layers, still falling inward at a significant fraction of the speed of light, slam into the bounced core. A shockwave propagates outward. The shockwave moves outward through the still infalling outer core material. As it moves through dense material, it loses energy, dissociating iron nuclei back into their component protons and neutrons, consuming energy with every iron nucleus it encounters. The shockwave stalls. It does not immediately succeed in ejecting the outer layers. What revives it? This is still an area of active research, but the leading mechanism involves the neutrinos. The collapse of the iron core produces a brief but extraordinarily intense burst of neutrinos. More neutrinos are emitted in that fraction of a second than the Sun will emit across its entire 10 billion year lifetime. Even though neutrinos interact very weakly with matter, there is so much material surrounding the stalled shock that a tiny fraction of the neutrino energy is deposited behind the shock wave, reviving it. The shock wave regains energy and begins to move outward again. When the shock wave reaches the surface of the star explodes. The outer layers are ejected at speeds of up to 30,000 kilometers per second, 10% of the speed of light. The explosion releases an enormous amount of energy, roughly 10 to the power of 44 joules of energy in kinetic energy and light combined. The energy released in neutrinos alone is about 100 times larger, 10 to the power of 46 joules. But most of it streams through the star and into space essentially invisibly. In the most luminous supernovae, the optical emission alone can briefly match or exceed the luminosity of an entire galaxy of hundreds of billions of stars. A single stellar death briefly, outshining billions of suns simultaneously. For the largest stars, the supernova explosion can be even more extreme, a hypernova, with kinetic energies 10 to 100 times greater than a conventional core collapse supernova. These may be accompanied by gamma-ray bursts, the most energetic events in the observable universe. After the explosion, what remains? The answer depends on how much mass is in the core remnant after the explosion. For standard massive stars in the range of 8 to perhaps 20 or 25 solar masses, the remnant is a neutron star. A neutron star contains perhaps 1 to 2 solar masses in a sphere only 10 to 20 kilometers in diameter. The density is comparable to atomic nuclei. A cubic centimeter of neutron star material would weigh roughly 1 billion tons on Earth's surface. Not 1 billion tons crushed to the size of a sugar cube in some abstract sense. A single sugar cube of neutron star material would weigh 1 billion tons. Neutron stars are supported against further collapse by neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being compressed into the same quantum state. They rotate. In many cases, they rotate very rapidly. As the iron core collapsed from roughly Earth size to neutron star size, conservation of angular momentum caused it to spin up, just as a figure skater spins faster when pulling their arms inward. Some neutron stars rotate hundreds of times per second. These are called millisecond pulsars. They emit beams of radio waves that sweep across space as the star rotates, creating pulses that reach us with clockwork regularity. For the most massive progenitor stars, those that retain cores above roughly 3 solar masses at the moment of collapse, neutron degeneracy pressure is not enough. The collapse continues past the neutron star stage. No known force can halt the collapse. What remains is a black hole. For stars in the mass range of the largest known hypergiants, those with 100, 200 or more solar masses, the situation is more complex still. Mass loss through stellar winds over their lifetimes may have stripped these stars down to considerably lower masses by the time they explode. The remnant could be a neutron star, a black hole, or, for the most extreme cases, the collapse might be so complete that the supernova fails entirely and the star collapses directly to a black hole without a visible explosion. One moment, a brilliant supergiant exists. The next, there is simply a black hole where the star was. Some theoretical models suggest that the most massive stars, those with initial masses above perhaps 250 solar masses, may undergo a different kind of death altogether. At the extreme temperatures and densities in the core of such a massive star near the end of silicon burning, the gamma-ray photons produced by the burning have enough energy to spontaneously create electron-positron pairs. This process, called pair instability, removes pressure support from the core without releasing energy. The core begins to collapse. But unlike a standard core collapse supernova, the collapse triggers explosive oxygen and silicon burning so intense that the energy released halts the collapse and drives an outward explosion before any compact remnant can form. This is called a pair instability supernova. It is predicted to be dramatically more energetic than a conventional core collapse supernova. The entire star can be disrupted, with no remnant at all. Every atom that made up the star is expelled into space. The heaviest elements synthesized in the explosion, including large quantities of radioactive nickel-56, are scattered across the surrounding region, eventually decaying into iron. Pair instability supernovae have been proposed as explanations for several observed transients, events called superluminous supernovae or superluminous SNE, that are 10 to 100 times more luminous than conventional supernova. One candidate is SN2006GY, which occurred in the galaxy NGC 1260 about 238 million light-years away, and reached a peak luminosity of roughly 50 billion solar luminosities. Another is SN2007BI, which showed signatures consistent with a pair instability supernova of a very massive star. These are the deaths of the largest stars. Not quiet fades, not gentle white dwarf cooling. Pair instability supernovae, hypernovae, gamma-ray bursts, or simple disappearances into black holes. The largest stars die as violently as they lived. Let's spend time on gamma-ray bursts because they represent the most extreme endpoint in the death of the most massive stars. And they illustrate better than almost anything else just how extreme the upper end of the stellar mass spectrum is. A gamma-ray burst is a brief but extraordinarily intense flash of gamma radiation, the most energetic form of electromagnetic radiation. The shortest gamma-ray bursts last a fraction of a second. The longest last several minutes, or occasionally longer. In that brief time, a single gamma-ray burst releases more energy than the sun will emit across its entire 10 billion year lifetime. Let's sit with that a few seconds. 10 billion years of solar energy. The energy released in a gamma-ray burst, approximately 10 to the power of 44 joules for a typical long-duration event, is comparable to the total kinetic energy of a supernova explosion, but released not as a spherical blast, but in a tightly collimated beam, like a laser rather than a bomb. This collimation focuses the energy, making the burst detectable across the observable universe. Gamma-ray bursts have been observed at distances of more than 13 billion light-years, occurring when the universe was less than 1 billion years old. The long-duration gamma-ray bursts, those lasting more than about 2 seconds, are associated with the deaths of massive stars. The leading model is called the collapsar model, developed primarily by the astrophysicist Stan Woosley. In this model, a rapidly rotating massive star collapses to form a black hole. As material falls toward the newly formed black hole, it forms an accretion disk around it. The black hole consumes this material at an enormous rate. And the combination of the rotating black hole and the magnetic fields threading through the disk launches 2 relativistic jets perpendicular to the disk, beams of material and energy moving at speeds of 99.999% of the speed of light or faster. These jets, called relativistic jets, punch through the remaining outer layers of the dying star and emerge from the poles. When the jet reaches low enough density material, it produces a gamma-ray burst visible across the universe. The jet carries an energy density so extreme that the matter within it is moving relativistically, generating shock waves that accelerate electrons to ultra-relativistic energies. And those electrons radiate through a process called synchrotron radiation, producing the observed gamma rays. After the initial burst fades, the jet continues interacting with the surrounding interstellar medium, producing a longer duration afterglow at progressively longer wavelengths, from X-ray to optical to radio. These afterglows have been observed for days, weeks, and in some cases months after the initial burst. The short-duration gamma-ray bursts, those lasting less than 2 seconds, are associated with different events. The merger of 2 neutron stars, or a neutron star merging with a black hole. These mergers are a completely different story, connected not to the deaths of the largest individual stars, but to the deaths of neutron star binaries. The gravitational wave event GW 170817, detected on August 17, 2017, combined with its electromagnetic counterpart observed across the spectrum, provided the first confirmed observation of a neutron-star merger and its associated gamma-ray burst. It also confirmed that neutron-star mergers are a site of our process nucleosynthesis, the rapid neutron capture process that produces about half of the elements heavier than iron in the universe, including gold, platinum, and uranium. The gold in your jewelry was forged in the collision of two neutron stars. But we were discussing the largest stars and their long-duration gamma-ray bursts. If a gamma-ray burst is aimed at Earth and occurs within a few thousand light-years of us, the effects could be severe. The gamma radiation ionizing the upper atmosphere, producing nitric oxide that would destroy the ozone layer over an extended period. Estimates suggest that a gamma ray burst within 1 to 2 kiloparsecs, about 3,000 to 6,500 light-years, aimed directly at Earth, could destroy enough of the ozone layer to cause a mass extinction comparable to those in the geological record. Some researchers have proposed that the late Ordovician mass extinction, which occurred approximately 443 million years ago and wiped out about 85% of marine species, may have been triggered or exacerbated by a nearby gamma-ray burst. This remains speculative and controversial, but it's not scientifically implausible. The good news is that gamma-ray bursts are extraordinarily rare events, even on astronomical timescales. In a galaxy the size of the Milky Way, they occur on average perhaps once every few 100,000 to few million years. The probability of one occurring close to Earth and aimed directly at us in any given human lifetime is extraordinarily small. And the Milky Way, being a relatively low metallicity star-forming environment in its outer spiral arms where we reside, is not an optimal location for producing the rapidly rotating massive stars that generate gamma-ray bursts. Galaxies with lower metallicity and more intense star formation are more likely to produce them. We are, in this regard, relatively fortunate in our cosmic address. Where do these monsters come from? What kind of environment produces stars of 100, 200 or more solar masses? Stars form from the collapse of giant molecular clouds, regions of the interstellar medium where hydrogen gas is cold enough and dense enough to be in molecular form rather than atomic form, where temperatures are only a few tens of degrees above absolute zero, and number densities of molecules are perhaps 100 to 100,000 per cubic centimeter. These clouds can contain millions of solar masses of material spread across hundreds of light years. The most massive stars form in the densest, most turbulent regions of molecular clouds, where the local density is high enough and where turbulent compression events trigger rapid collapse. The Jeans mass. The minimum mass a cloud fragment needs to be unstable to gravitational collapse is lower in denser and cooler regions. So these conditions favor the formation of many stars over a wide range of masses. But the specific process by which the most massive stars accumulate such enormous masses is still a subject of active research. There are competing theories. In one scenario, massive stars form through the same basic process as lower mass stars, gravitational collapse of dense cloud cores. But in regions where the cores are particularly massive. In another scenario, massive stars grow through competitive accretion. where a protostar sitting in a dense cloud environment continues to accumulate material from its surroundings long after lower mass stars nearby have exhausted the local reservoir. In a third scenario, massive stars form through the merger of several less massive protostars in very dense environments. What's clear is that massive stars tend to form in clusters, not in isolation. The most massive stars in the universe are almost always found in rich stellar clusters, where dozens or hundreds of massive stars formed simultaneously from the same molecular cloud. R136 in the Tarantula Nebula is a spectacular example. It contains dozens of very massive stars within a few light years of each other, all formed from the same dense region of the Tarantula Nebula's molecular cloud, all within roughly 1 million years of each other. The formation of these clusters of massive stars is self-limiting in a dramatic way. The ultraviolet radiation and stellar winds from the most massive stars rapidly disperse the surrounding gas and dust from which additional stars might form. Within perhaps 1 million years of the formation of the most massive stars, the molecular cloud from which they formed has been so thoroughly disrupted by their radiation and winds that star formation in the region essentially ceases. The massive stars have consumed and destroyed the raw material for additional star formation. This feedback between massive star formation and molecular cloud destruction is one of the most important regulatory mechanisms in galactic star formation. Without it, molecular clouds would form stars much more efficiently, converting a much higher fraction of their mass into stars on a much shorter timescale. The disruptive feedback from massive stars regulates the overall star formation rate in galaxies. The Tarantula Nebula provides a spectacular demonstration of this process in action. The central cluster R136, containing dozens of extremely massive stars, has carved a cavity in the surrounding gas. The ionized region around R136 extends for hundreds of light years in every direction. The edges of this region, where the intense radiation and winds slam into the surrounding molecular cloud, are regions of compressed gas where triggered star formation is occurring. New stars being born at the boundary between the ionized region and the undisturbed molecular cloud. The most massive stars are simultaneously destroying the raw material for new stars and triggering the formation of new stars at the boundary of the region they're disrupting. We've been talking about how massive stars die. But their deaths are not endings. They are, in a fundamental sense, the most important contributions these stars make to the ongoing story of the universe. When a massive star explodes as a supernova, it doesn't just release energy, it ejects matter. The outer layers of the star, enriched with the products of all the nuclear burning stages it went through during its life, are thrown outward at speeds of 10 to 30,000 kilometers per second. This material mixes with the surrounding interstellar medium. It enriches the gas with elements that didn't exist in abundance before the star formed. The most massive stars, burning hottest and fastest, process the most material in the shortest time. In their brief lives, they take hydrogen and helium and convert it into carbon, oxygen, neon, magnesium, silicon, sulfur, and iron. In their deaths, they scatter all of this material across the galaxy. Every carbon atom in every living organism on Earth was forged in the core of a star. The carbon in your body's organic molecules, the carbon backbone of proteins and DNA, was synthesized through the triple alpha process in the cores of stars that lived and died before the solar system formed. Those stars exploded. Their carbon spread through space. Eventually, some of it ended up in the molecular cloud that collapsed to form the solar system. Some of it ended up in Earth. Some of it ended up in you. The oxygen you breathe was forged in stellar interiors. Oxygen is the third most abundant element in the universe after hydrogen and helium, and it's produced primarily in the cores of massive stars through helium burning and in the oxygen-burning shell of evolved massive stars. Every breath you take is made possible by the deaths of stars. The iron in your blood, the iron in the hemoglobin molecules that carry oxygen from your lungs to every cell in your body, was produced in the iron core burning stage of massive stars and in the supernova explosions that scattered it into space. The iron in your red blood cells is recycled stellar material. The silicon in the rocks under your feet, the magnesium and calcium in your bones, the phosphorus in your DNA, the sulfur in the proteins that define your body's structure. All of these elements were synthesized in stellar interiors and delivered to Earth through supernova explosions of stars that lived and died before the sun was born. Carl Sagan famously said that we are made of star stuff. This is not poetry or metaphor. It is chemistry. It is nuclear physics. It is the actual process by which every atom in your body was created. You are the downstream product of stellar nucleosynthesis. The atoms that make you are recycled material from stars that burned and died billions of years before Earth existed. The largest stars, the ones we've been describing tonight, are the most efficient processors of this raw material. Their extreme temperatures and pressures drive nuclear burning faster and more thoroughly than any other class of star. They enrich the interstellar medium with heavier elements more rapidly than lower-mass stars. The early universe, in the first billion years, was extremely low in heavy elements. Almost everything was hydrogen and helium, the products of Big Bang nucleosynthesis. The first generation of massive stars converted some of that hydrogen and helium into heavier elements and distributed them through supernova explosions. Each subsequent generation of stars formed from material enriched by the previous generation's deaths. Each supernova added more heavy elements to the galactic soup. Gradually, over billions of years, the interstellar medium became enriched enough that rocky planets could form. Planets with silicon oxygen rock and iron cores and water and the carbon compounds necessary for organic chemistry. The solar system formed from material enriched by the deaths of perhaps dozens or hundreds of generations of massive stars over the 4 billion years before the sun's birth. The most massive stars among those predecessors processed the most material most rapidly, contributing the most to the heavy element budget of the galaxy. You exist because massive stars burned hot, burned fast, and died violently. Their deaths created the material from which you are made. Their violence was the necessary precondition for your existence. Let's bring this home. Let's replace our sun, one by one, with the stars we've described tonight, and think through what would actually happen to our solar system. Replace the sun with UY Scuti. UY Scuti has a radius of approximately 1,700 solar radii. If it were placed at the center of our solar system, its surface would extend past the orbit of Jupiter. Mercury, Venus, Earth, Mars, and all the asteroids in the asteroid belt would be inside the star. Jupiter would be just below the stellar surface or just at it, depending on the exact radius estimate. The outer planets, Saturn, Uranus, Neptune, and Pluto, would be outside the star's surface, but deep within its extended atmosphere. The word atmosphere here is key. Red supergiants are not dense, sharp-edged objects like the Sun or like Earth. They are extraordinarily diffuse in their outer layers. The density of a red supergiant's atmosphere at its nominal surface is roughly comparable to, or less than, a laboratory vacuum on Earth. The outer layers of UY Scuti have densities thousands of times lower than the best vacuum chambers we can create. If you were to somehow stand in the outer layers of UY Scuti without being incinerated, the material around you would be thinner than the thinnest air you've ever breathed. But incinerated is the key word. Even this diffuse material has a temperature of approximately 3,400 degrees Kelvin, and the total luminosity of UY Scuti is somewhere around 340,000 times the Sun's luminosity. This radiation is what matters for the fate of any surviving planets. The energy received by an object at a given distance from a star scales with the star's luminosity and the inverse square of the distance. At the distance of Jupiter's current orbit, roughly 5.2 astronomical units from the Sun, an object receives 340,000 times more energy from UY Scuti than it currently receives from the Sun. Jupiter's cloud tops, currently at about -145 degrees Celsius, would receive energy comparable to what a planet would receive if it were orbiting a normal sun at roughly 1% of Earth's current orbital distance. The equilibrium temperature for Jupiter's atmosphere would be extraordinarily high. Its hydrogen and helium atmosphere would begin to be stripped away. Saturn, Uranus, Neptune would all be exposed to radiation levels thousands of times greater than anything they currently receive. All of their atmospheres would be dramatically altered. Earth? Earth is inside the star. Earth does not exist as a separate object anymore. The material at Earth's current orbital radius is stellar plasma. Replace the Sun with R13601. R13601 has a radius of about 35 solar radii, so physically much smaller than UY Scuti. Earth would still exist as a planet, not engulfed. But the luminosity of R136A1 is approximately 8.7 million times the Sun's luminosity. Earth, at its current orbital distance, would receive 8.7 million times more energy from R13601 than it currently receives from the Sun. The equilibrium surface temperature of a planet scales as the fourth root of the received energy. If we scale up the energy by 8.7 million, the fourth root of that is approximately 54. Earth's current equilibrium temperature, very roughly 255 Kelvin, including the greenhouse effect, multiplied by 54, gives approximately 13,770 Kelvin, 13,770 degrees. That is hotter than the surface of the Sun. Earth's surface would be completely vaporized. Not just the oceans, not just the atmosphere. The rocks, the iron core, the entire crust, mantle, and core would vaporize. Within days of replacing the Sun with R13601, Earth would cease to be a solid object and would become a cloud of superheated plasma distributed along its former orbit. The habitable zone around R13601, the distance at which a planet might have liquid water on its surface, would be roughly at the square root of 8.7 million times Earth's current orbital distance. That's approximately 2,950 times the Earth-Sun distance, 2,950 astronomical units. The outer edge of the solar system, the heliopause where the solar wind gives way to interstellar space, is at about 120 astronomical units. R13601's habitable zone would be 25 times farther from the star than our solar system's edge. There are no known planets at 2,950 astronomical units in our solar system. Even the Oort cloud, the distant shell of icy objects that begins perhaps at 2,000 to 5,000 astronomical units, is at the inner edge of the region, where water might be liquid around R13601. Replace the Sun with Eta Carinae. Eta Carinae's primary star, Eta Carinae A, has a luminosity of approximately 5 million solar luminosities. The habitable zone calculation gives roughly 2,236 astronomical units. Similar to R13601. Earth vaporized, inner solar system destroyed, habitable zone in the outer reaches where only the most distant icy bodies currently reside. But Eta Carinae is also actively erupting and unstable. The second body in the binary system, Eta Carinae B, with perhaps 1 million solar luminosities, adds to the radiation field. The combined system's radiation, plus its powerful, fast stellar wind, would have swept away any planetary atmosphere within its habitable zone long before any life could develop. Eta Carinae B's ultraviolet output alone is so intense that any planet at the theoretical habitable zone distance would be continuously bathed in sterilizing radiation. These stars do not have habitable zones in any practical sense. The radiation environment is too extreme, the stellar lifetimes too short, the variability too dramatic. Any planet orbiting one of these stars within the first million years of their lives would be incapable of supporting life as we know it. The stars burn too fast, vary too dramatically, and die too violently. The stars we've described tonight are all located in our galactic neighborhood or in the large Magellanic Cloud, a satellite galaxy. But the Milky Way is 100,000 light years across, and the observable universe contains 2 trillion galaxies. How many more extreme stars are out there that we haven't discovered? The answer is many, and probably more extreme. Observationally, our ability to detect and characterize the most massive and most luminous stars is limited by distance and by dust. Dust in the interstellar medium absorbs and scatters optical light, making distant or dust-embedded stars difficult to study in visible wavelengths. Many massive stars form in the dense, dusty hearts of molecular clouds that are opaque to optical telescopes. Infrared and radio observatories can penetrate this dust, but have lower resolution and sensitivity for characterizing individual stars at great distances. Within the Milky Way, the central regions are particularly obscured. The galactic center, home to a dense population of massive stars, is hidden behind many kiloparsecs of intervening dust. We observe the galactic center primarily in infrared and radio wavelengths, and even these observations are limited. There may be stars in the galactic center that exceed in mass or luminosity anything we've cataloged. In other galaxies, particularly in starburst galaxies undergoing episodes of extremely intense star formation, the most massive stars may be far more extreme than anything we've observed. Starburst galaxies are producing stars at rates hundreds or thousands of times greater than the Milky Way. The most active starburst episodes can produce dense clusters comparable to or exceeding R136 in the Tarantula Nebula. But at distances of millions or hundreds of millions of light years, where individual stars cannot be resolved with current telescopes. The theoretical upper limit on stellar mass is not well established. Early estimates, based on the Eddington luminosity limit, suggested that stars above about 150 solar masses could not be stable, that radiation pressure would simply prevent the formation of such objects by dispersing the infalling material before it could accumulate. But the discovery of stars like R13601, which appear to exceed this limit significantly, shows that the theoretical picture is incomplete. stars can form and exist with masses well above the old Eddington limit, at least briefly. Current theoretical estimates suggest that the upper mass limit for a star might be somewhere between 300 and 1,000 solar masses, depending on conditions during formation. Whether stars at the extreme upper end of this range actually exist in the observable universe is unknown. If they do, their properties would be extraordinary, even by the standards of the objects we've discussed tonight. A star of 1,000 solar masses, if it could exist, would have a luminosity of perhaps 40 to 60 million solar luminosities. It would be so luminous that it would be near the very edge of gravitational stability, losing mass at an almost incomprehensibly rapid rate. Its lifetime might be measured in hundreds of thousands of years rather than millions. Its death would release energy correspondingly extreme. Theoretical predictions suggest it might undergo a pair instability supernova, disrupting itself completely, leaving no remnant, scattering all of its material into space in one of the most energetic explosions the universe is capable of producing. Whether any such star has ever existed and what we might observe if one died within the observable universe today are open questions. The universe's most extreme phenomena may still lie beyond our current catalog. We've been talking about scale throughout this exploration, building from the sun to stellar monsters hundreds of times more massive and millions of times more luminous. Let's step back and think about what this scale tells us about the universe. The universe contains objects across an enormous range of scales. From the Planck length, the smallest meaningful distance in current physics at about 10 to the minus 35 meters, to the observable universe at about 8.8 times 10 to the 26 meters. The range spans more than 60 orders of magnitude. Within this range, the objects we think of as large in everyday life, mountains, planets, stars, galaxies, occupy a tiny fraction of the total scale. But within the stellar mass range, the variation is itself enormous. From the least massive hydrogen-burning stars at about 0.08 solar masses to our 13601 at perhaps 200 solar masses, the mass range spans a factor of about 2,500. In terms of luminosity, the range is far more extreme. The least luminous main sequence star has a luminosity of perhaps a few 10,000ths of the sun's luminosity. Our 13601 has a luminosity of nearly 9 million solar luminosities. The range in luminosity across the stellar main sequence spans roughly 11 orders of magnitude, 100 billion times from least to most. This enormous range of properties means that the universe is anything but uniform. It's not a place where everything is average and variation is small. It's a place where the same physical process, the gravitational collapse of gas and subsequent nuclear fusion, produces objects ranging from dim red sparks barely massive enough to sustain fusion, burning for trillions of years, to blazing blue behemoths that live fast, burn bright, and die in the most violent explosions nature can produce, all within the span of a few million years. The range of stellar fates is correspondingly extreme. Red dwarfs will burn steadily until the universe is many times its current age. Their fuel consumes so slowly that none have ever died naturally. Sun-like stars have 10 billion-year lives, dying gently as white dwarfs. Massive stars live briefly and die violently, leaving behind neutron stars, black holes, or nothing at all. This diversity is not arbitrary. It arises from a relatively small number of physical laws: quantum mechanics, thermodynamics, nuclear physics, and general relativity, operating on matter under a range of initial conditions. The same rules, applied to different amounts of matter, produce radically different outcomes. This is one of the most profound things the study of stars reveals about the universe. simple rules can generate enormous complexity and diversity. One of the implicit questions that hangs over any discussion of the most massive stars is whether life could exist near them. We've established that the habitable zone around these stars would be at enormous distances and that the radiation environment would be extreme. But let's think more carefully about what the existence of such stars means for the question of life in the universe. Life on Earth took roughly 4 billion years to progress from the first self-replicating chemistry to technological civilization. 4 billion years is a reasonable estimate for the time complexity requires. Though we don't know whether this is a universal minimum or whether Earth's timeline was unusually slow or fast. The most massive stars live for 2 to 3 million years. That is less than 1% of the time it took life on Earth to reach technological complexity. A planet orbiting near a star like R13601 at the theoretical habitable distance of 2,950 astronomical units would receive intense ultraviolet radiation from the start. The star would explode in its core collapse event after 2 or 3 million years. A planet at that distance would survive the death of the star, as the shock wave from the supernova would take millions of years to reach it and would be extremely dilute by that distance. But the gamma radiation from any associated gamma ray burst could be significant. More fundamentally, there simply isn't enough time. Even if the conditions around such a star were somehow perfectly suited to life, 2 to 3 million years is not enough time for the chemistry of life to emerge, develop, and evolve. By the time the chemistry of life was underway, the star would be dead. This has a profound implication. The universe's most massive stars, the ones with the most dramatic existences and the most violent deaths, are fundamentally incompatible with life as we know it. Not because they're hostile, though their radiation environments certainly are, but because they don't exist long enough. Life requires patience, billions of years of stable conditions, billions of years of consistent sunlight and stable stellar luminosity, and a planet that can evolve complex chemistry without being disrupted. The stars that provide these conditions are not the most dramatic stars. They are the modest, long-lived stars, the G-type stars like our Sun, the K-type orange dwarfs, the red dwarfs with their multi-trillion-year lifespans. The most massive stars contribute to the conditions for life not by hosting it, but by enriching the interstellar medium with the heavy elements that rocky planets and biological chemistry require. They live briefly, burn furiously, synthesize heavy elements, and scatter them through their deaths. They are the heavy element factories that made Earth's chemistry possible. Without their deaths, there would be no carbon, no oxygen, no iron, no silicon. Without their deaths, Earth would not be rocky. Without their deaths, life as we know it could not exist. The largest stars are generators of the raw material for life, not hosts of it. Let's put everything we've discussed into a unified timeline, because the contrast in timescales is one of the most striking features of the stellar mass spectrum. The universe is approximately 13.8 billion years old. A red dwarf star of 0.1 solar masses, formed when the universe was 1 billion years old, will burn for an additional 10 trillion years. It has experienced less than 0.13% of its lifetime so far. When the universe is 1,000 times its current age, this star will still be burning. Our Sun, formed 4.6 billion years ago, will exhaust its core hydrogen in about 5 billion years. It will then swell to a red giant, shed its outer layers, and leave behind a white dwarf that will cool over trillions of years. Our Sun's total active lifetime is about 12 billion years. A star of 10 solar masses formed 4 billion years ago would have burned for perhaps 20 million years and exploded as a supernova roughly 3.98 billion years ago. The neutron star, or black hole it left behind, is still out there somewhere, cooling slowly, orbiting the galaxy. A star of 30 solar masses, with a lifetime of about 5 million years, formed 5 million years ago, was born after our Sun and died before the earliest dinosaurs walked the Earth. R13601, with an age of about 1 million years, was born when our ancestors in the genus Homo were already making stone tools. When it dies, in perhaps another 1 to 2 million years, our descendants, whatever they have become, may witness its death from Earth. Eta Carinae, with its instability and evolutionary advancement, may explode within the next 100,000 years, within the span of time that modern humans have existed. These timescales span 13 orders of magnitude, from the lifetimes of the most massive stars in the millions of years to the lifetimes of red dwarfs in the trillions of years. Within a single universe, stars are born and die on timescales ranging across a factor of 1 million. And the universe itself, 13.8 billion years old, is in some respects young. It has fuel for stars for many more billions of years. The era of stellar burning, the stelliferous era as some cosmologists call it, began a few 100 million years after the Big Bang and will last perhaps 100 trillion years, until the last red dwarf has burned its last hydrogen. We are only 0.014% of the way through the stelliferous era. Part 21. The stars that shaped history without knowing it. The most massive stars that have ever existed died billions of years ago. They have no memory of existing, no awareness of what they accomplished. But their deaths shaped everything. The first generation of stars in the universe, called Population 3 stars, formed from pure hydrogen and helium, less than 1 billion years after the Big Bang. There were no heavy elements, no carbon, no oxygen, no silicon, no iron. Nothing beyond hydrogen, helium, and trace amounts of lithium. These were the raw products of Big Bang nucleosynthesis. Population 3 stars were likely extremely massive by the standards of later stellar generations. Without heavy elements in the gas from which they formed, the gas could not cool as efficiently, and higher mass clouds were needed to collapse under gravity. Theoretical models suggest Population 3 stars may have been predominantly in the range of 100 to 1,000 solar masses. They were all O-type stars, all hypergiants by modern standards, all blazing with extreme ultraviolet radiation. They lived for only a few million years at most, and then they died. Their supernovae, hypernovae, and pair instability explosions scattered the first heavy elements into the intergalactic medium. For the first time in cosmic history, the gas between galaxies and within early galaxies contained carbon, oxygen, silicon, iron. For the first time, the raw material for rocky planets existed. The second generation of stars, Population 2 stars, formed from this slightly enriched material. They were still poor in heavy elements compared to modern stars, but they contained enough to cool their birth clouds more efficiently and to produce a wider range of stellar masses. Some of them were massive and died young, adding more heavy elements to the mix. Others were lower mass and still exist today, orbiting in the halos of galaxies as some of the oldest stars we can observe. Today's stars, Population 1 stars like our Sun, form from material enriched by many generations of stellar births and deaths. Our Sun contains about 2% heavy elements by mass, a fraction that reflects the cumulative contribution of billions of stellar deaths across more than 9 billion years of galactic history before the Sun formed. Every stage in this progressive enrichment was driven primarily by the deaths of the most massive stars. They were the principal factories. They were the quickest to process their fuel and return it to the interstellar medium. The red dwarfs forming at the same time as population 3 stars are still burning today, having contributed nothing to the heavy element enrichment of the universe. The massive stars are long gone, but their legacy is everywhere. You are their legacy. The rocky planet you live on is their legacy. The oxygen you breathe is their legacy. The carbon chemistry of every living thing on Earth is their legacy. The iron at the Earth's core that generates the magnetic field protecting your atmosphere is their legacy. Stars that lived and died before the sun was born left behind the material from which you are made. Their violence, their brief, blazing lives, their catastrophic deaths were the necessary preparation for your existence. Beyond their role in chemical enrichment and their dramatic deaths, the largest stars have taught us fundamental things about physics that we could not have learned any other way. The physics of very massive stars is a laboratory for conditions impossible to replicate on Earth. The temperatures and pressures in the cores of stars in silicon burning, reaching billions of degrees and densities of hundreds of tons per cubic centimeter, cannot be created in any terrestrial laboratory for any significant duration. The physics operating in these conditions, the rates of nuclear reactions, the behavior of matter at nuclear density, the properties of neutrino transport through dense plasma, can only be studied by observing the stars themselves and by modeling them theoretically. Neutrino physics received one of its greatest advances from a supernova. On February 23, 1987, a star in the Large Magellanic Cloud exploded as SN 1987A. This was the first supernova close enough to be observed in detail since the invention of the telescope, visible to the naked eye from the southern hemisphere. A few hours before the optical brightening was detected, neutrino detectors on Earth, the Kamiokande detector in Japan and the IMB detector in Ohio, detected a brief burst of neutrinos from the direction of the explosion. This confirmed, for the first time, the theoretical prediction that core collapse supernovae emit the overwhelming majority of their energy in neutrinos. The 25 neutrinos detected represent a tiny fraction of the roughly 10 to the power of 58 neutrinos emitted by the explosion, the majority of which passed through Earth without being detected. The comparison between the observed neutrino arrival time, energies, and duration and theoretical predictions constrained models of core collapse physics, neutrino mass, and the properties of neutrinos at high densities. SN 1987A continues to teach us. The shockwave from the explosion is still expanding, and as it encounters the rings of material shed by the progenitor star in an earlier evolutionary phase, it produces X-ray and radio emission that we can observe and model. The neutron star produced by the explosion has been searched for over the 37 years since the explosion, and recent James Webb Space Telescope observations have provided strong evidence for the existence of a neutron star at the center of the expanding nebula, consistent with theoretical predictions. Gravitational wave astronomy, born in 2015 with LIGO's first detection, is closely tied to the deaths of massive stars. The merging neutron stars and black holes that produce gravitational waves detectable from Earth are the remnants of massive stars. The properties of these remnants, their masses, spins, and orbital parameters, carry information about the physics of the massive stars from which they formed, the supernovae explosions that produced them, and the processes of binary stellar evolution that brought them to merger. Each gravitational wave event is a message from the death of massive stars, encoded in the geometry of space-time and readable in principle. in the tiny distortions of LIGO's mirrors. We are, as this field develops, reading the death notices of massive stars across billions of light years and billions of years of cosmic history. We've mentioned that there's an upper limit to stellar mass, but haven't fully explored what sets it. Let's do that now, because the physics of the upper mass limit is itself fascinating. The Eddington limit, as described earlier, sets the luminosity at which radiation pressure equals gravity for a given mass. For a uniform composition star of standard composition, the Eddington luminosity scales linearly with mass. Double the mass, double the Eddington luminosity. Stars near the Eddington limit are unstable because small perturbations can push them above it, triggering mass loss. For a long time, it was thought that the Eddington limit translated to a maximum stellar mass of roughly 120 to 150 solar masses, because stars above this mass would have luminosities exceeding the Eddington limit and would immediately begin losing mass rapidly enough to prevent further growth. The discovery of stars like R13601 seemingly exceeded this prediction. The resolution involves a more careful treatment of the Eddington limit that accounts for the fact that radiation is not absorbed uniformly throughout a star. In the outer layers of very massive stars, where the material is hot enough to be significantly ionized, and where radiation pressure is most important, the ratio of radiation force to gravitational force is sensitive to the local opacity of the material. In regions where the opacity is particularly high, perhaps due to ionization edges where the opacity spikes as a new ionization state becomes available, the local Eddington limit can be exceeded even when the global stellar luminosity is below the global Eddington limit. This leads to instabilities called strange mode instabilities, and to pulsations and mass loss from the outer layers. Very massive stars near the Eddington limit are constantly pushing against their own stability boundary, losing mass through pulsation-driven winds and occasional larger eruptions. This is precisely what we see in luminous blue variables, like Eta Carinae. Whether there is a true maximum stellar mass depends on the competition between mass gain during formation and mass loss through winds and instabilities. Current observations and theories suggest that the maximum mass for a star that can form and persist for a significant fraction of its main sequence lifetime is perhaps 200 to 300 solar masses. Above this range, the mass loss during formation would prevent the protostar from growing further, or the mass loss rate during the main sequence would rapidly reduce the star's mass to below the unstable regime. But the physics is not completely settled. Different theoretical approaches give somewhat different predictions, and the observational sample of the most massive stars is small, subject to significant measurement uncertainties, and likely incomplete because the most massive stars are both rare and often embedded in dusty regions difficult to observe in optical wavelengths. The upper mass limit for stars is one of those areas of astrophysics where the uncertainty is real. The question is important, and the answer is still being worked out. There's a poetic truth buried in everything we've discussed tonight. When you look at the night sky, you're looking at a graveyard and a nursery simultaneously. The stars you see are not permanent. They are in process. They are in the middle of their lives, some near the beginning and some near the end. The most dramatic ones, the brightest ones in many cases, are the most massive ones, and therefore the ones closest to their ends. Betelgeuse, the bright red star in the shoulder of Orion, is a red supergiant of approximately 15 to 20 solar masses. It's one of the largest stars visible to the naked eye, with a radius of perhaps 700 to 1,000 solar radii. It's variable, pulsating with periods of several years, losing mass through a powerful stellar wind, and is generally considered to be in a late evolutionary phase. When it explodes, it will be visible from Earth in daylight. It could happen in 100 years. It could happen in 100,000 years. Rigel, the blue-white star in Orion's foot, is a blue supergiant of perhaps 21 solar masses, with a luminosity of about 120,000 solar luminosities. It's much hotter and less evolved than Betelgeuse, but it too will eventually exhaust its nuclear fuel and explode. The Orion constellation, which has been used as a navigational reference since antiquity, contains within it several stars destined to explode as supernova within the next few million years. The nebula at the heart of Orion, the Orion Nebula visible as a fuzzy patch in Orion's sword, is a star-forming region where massive stars are being born right now. Orion simultaneously contains massive stars in their final pre-supernova evolutionary phases and the nursery where the next generation of massive stars is forming. The galaxy is in continuous process. Stars are always being born. Stars are always dying. The supernova remnants of previous stellar deaths are expanding through the interstellar medium, enriching the gas, compressing molecular cloud boundaries, triggering new star formation at the edges of the expanding shells. The births and deaths are linked in a continuous cycle that have been operating for 13 billion years and will continue for billions more. The material in the Orion Nebula, the gas and dust currently condensing into new stars, contains heavy elements produced by generations of massive stars that lived and died before the Sun formed. The stars forming in Orion today are made partly of material that was once inside stars that have already exploded. Some of those stars may form planets. Some of those planets may eventually, given time, find themselves in habitable conditions. The violence of the largest stars is the precondition for everything that follows. Their deaths are not endings. They are the mechanism by which the universe prepares the material for the next cycle. Let's end where we began, with scale. Because after everything we've discussed, the scale is still the most important thing. Our Sun, a star 109 times Earth's diameter, containing 1.3 million Earths within it, is not small. It is the dominant object in the solar system. It contains 99.86% of all the mass in everything that orbits it. Its gravity holds Neptune in its orbit 4 billion kilometers away. Its light reaches us in 8 minutes after traveling 150 million kilometers of vacuum. Its hydrogen fusion has been burning steadily for 4.6 billion years and will continue for another 5 billion. And yet, placed next to UY Scuti, the Sun is a marble. UY Scuti's radius is 1,700 times the Sun's radius. In volume, UY Scuti contains roughly 5 billion suns. 5 billion suns worth of volume in a single star. Placed next to the Tarantula Nebula, the Sun is a point of light among tens of thousands of others, all forming simultaneously from the same cloud of gas. Many of them far more massive and far more luminous than our quiet, modest star. And the Tarantula Nebula, impressive as it is a single star-forming region in a single satellite galaxy of the Milky Way. The Milky Way contains hundreds of billions of stars. The observable universe contains 2 trillion galaxies. Each galaxy contains hundreds of billions or more stars. The numbers are so large they lose all meaning in ordinary language. But within that vastness, within those 2 trillion galaxies and those uncountable stars, the largest and most massive represent the most extreme end of what the universe does with matter under gravity. They are the universe operating without restraint, packing as much mass as possible into a star, burning it as fast as the laws of physics allow, and dying in the most dramatic way possible. They are terrifying because they reveal what the universe is capable of. Because they show that the gentle, patient burn of our sun is not the only mode the universe knows. The universe also knows fury. The universe also knows extremes that reduce everything familiar to nothing. And it does this constantly, across 2 trillion galaxies, at every moment, without exception, without pause, without regard for anything in its path. The largest stars in the universe are not anomalies. They are a recurring feature of a universe that operates across an enormous range of scales and intensities. They are what happens when gravity has access to hundreds of solar masses of material. They are what happens when nuclear physics operates under conditions of extreme temperature and pressure. They are what happens when the universe takes the same basic process that produces our sun and amplifies it until the result is barely stable, barely containable, burning itself out in a fraction of the time it would take a modest star to notice the change. They are born, they burn, they die. And in dying, they create the conditions for everything else, including us. Tonight we met stars that dwarf our imagination. Stars whose surfaces extend to where Jupiter orbits. Stars that outshine entire galaxies for a few billion seconds at the moment of their deaths. Stars that synthesize in their cores and the elements that make you what you are. The night sky looks the same after learning this as it did before. The stars are the same distance away. The same photons reach your eyes. Nothing has changed. And yet, nothing is the same. Because now when you see Betelgeuse reddening in the shoulder of Orion, you know it for what it is. A dying giant. A star that has exhausted its core hydrogen and is in the late stages of stellar evolution, expanding, pulsating, shedding mass, approaching the end that will come whether we are here to watch it or not. Because now, when you see the Milky Way as a band of light across the sky on a dark night, you know that band contains stars at every stage of their existence. Some just forming from molecular cloud collapse, some in the stable middle of their hydrogen-burning lives, some in the final 1,000 years before their iron cores collapse, some already dead, having left behind the neutron stars and black holes that dot the galaxy invisibly. Because now when you breathe, you know the oxygen entering your lungs was forged in the interior of a massive star that exploded billions of years ago, and that the iron in the hemoglobin carrying that oxygen through your blood is recycled stellar material from a death that predated Earth's formation. The largest stars in the universe are not distant curiosities. They are part of your story. Their violence is written into your chemistry. Their deaths produce the raw material of your existence. You are, in a very real and testable sense, the downstream product of stellar mass, stellar fusion, and stellar death. The universe is not obligated to be hospitable. It is not built to scale with human comfort or human intuition. It operates across ranges of size, temperature, energy, and time that dwarf every familiar reference point. The largest stars are one expression of how far beyond the familiar the universe operates. They are the universe at its most extreme, its most powerful, its most violent, and in the only way that matters for us who came after, its most generative. Without them, we could not be here. With them, the universe becomes, for a few million years at a time, something extraordinary. Thank you for exploring this with me tonight. If this changed how you look at the night sky, if it made the stars feel more real and more extreme and more connected to your own existence, please take a moment to like the video and subscribe to the channel. These deep explorations take real care to put together, and your support makes them possible. The next time you look up and see a star, any star, remember what it is. A ball of gas held together by gravity, consuming itself through nuclear fusion. spending its existence in a continuous battle between the energy trying to expand it and the gravity trying to collapse it. Some of those battles last trillions of years. Some last only a few million. All of them eventually end. And in ending, they give the universe what it needs to continue. Sleep well under a sky full of fires you never knew were burning for you.